What if the story of everything we know, every star, planet, and even the atoms that make up your body began with a single, unimaginable moment? The formation of the universe isn't just a tale of science. It's a profound mystery that has fascinated and perplexed humanity for centuries. From the explosive birth of time and space to the invisible forces shaping our existence, the origins of the cosmos hold secrets that stretch the limits of what we can understand. In this video, we're diving into 20 of the most captivating questions about the universe's formation, questions that not only challenge our knowledge but ignite our sense of wonder. What sparked the first spark? Could there have been anything before the beginning? And what role do dark matter and dark energy play in this vast cosmic puzzle? Prepare to uncover the mysteries of galaxies, the birth of stars, and the hidden forces binding everything together. Stay with us as we unravel the answers, or perhaps uncover even more questions that will forever change the way you see the universe. Now turning to our first question, what sparked the Big Bang? The Big Bang theory stands as the cornerstone of our understanding of the universe's origin, marking the moment when time and space as we know them came into existence. According to this theory, everything we see today, every galaxy, every star, every particle of matter, was once compressed into an unimaginably dense and hot point known as a singularity. But what exactly triggered this event? Here lies one of the greatest mysteries in cosmology. Some theories suggest that quantum fluctuations within this singularity could have set off the expansion, while others propose that the Big Bang could be part of a cycle, possibly the result of a collapsing universe that existed before our own. Still, others argue that the event may require no cause at all, existing as a fundamental law of nature beyond human comprehension. The idea that time itself began with the Big Bang adds another layer of complexity. If time did not exist before, then the very concept of a before the Big Bang becomes meaningless. This opens up a profound debate. Does the universe need a cause, or is our desire for causality simply a product of how we perceive reality? These questions challenge not only our scientific understanding, but also our philosophical perspectives on existence. And yet, as uncertain as we are about what sparked the first spark, one thing remains clear: the Big Bang set the universe in motion, paving the way for everything that followed. Moving forward, we ask an equally perplexing question: was there anything before the Big Bang? Moving forward, we delve into the question: was there anything before the Big Bang? This is often considered one of the most mind-bending questions in cosmology, as it challenges our understanding of time, causality, and existence itself. One of the leading theories is the idea of the multiverse, a concept suggesting that our universe could be just one of countless others, each with its own unique set of physical laws and conditions. According to this theory, the Big Bang might have been a localized event within a much larger multiversal framework, perhaps sparked by the collision or interaction of other universes. Another intriguing idea is the cyclical universe model, which proposes that the universe undergoes endless cycles of expansion and contraction. In this view, the Big Bang could have been the result of a previous universe collapsing into itself, leading to a rebirth of space and time as we know it. Prominent physicist Roger Penrose has even suggested a variation of this model, where the universe's distant future, dominated by dark energy and infinite expansion, could somehow seed the conditions for a new Big Bang. Then there is the hypothesis, backed by Stephen Hawking's work, that the universe may not need a beginning at all. Hawking proposed the idea of a boundary-less universe, where time itself behaves like a closed surface, rendering the question of before meaningless. In this scenario, the universe simply is. It has no origin as we traditionally understand it. Each of these ideas stretches the limits of our imagination and defies many of the fundamental ways we think about existence. While there is no definitive answer yet, these theories open up extraordinary possibilities about what might lie beyond the confines of our observable reality. As we continue our exploration, another question emerges. How did matter come to dominate over antimatter? Now turning to the next enigma, how did matter come to dominate over antimatter in the universe? This question dives deep into one of the most puzzling aspects of the cosmos. Based on our understanding of the Big Bang, matter and antimatter should have been produced in equal quantities. When these two types of particles come into contact, they annihilate each other, releasing energy in the process. So, logically, the universe should be filled with nothing but leftover energy, with no matter to form stars, planets, or even us. Yet, here we are, living in a universe overwhelmingly dominated by matter. Scientists believe the answer to this lies in a phenomenon known as baryogenesis. This is a theoretical process that could have occurred in the early universe, introducing a slight imbalance between matter and antimatter particles. The key idea is that certain interactions between particles during the universe's infancy might have favored the production of matter over antimatter ever so slightly. Even an incredibly tiny asymmetry, one particle of matter for every billion particles of antimatter, would have been enough to leave the surplus of matter we see today after all the annihilation processes took place. There are also theories suggesting that quantum fluctuations, which are random changes in energy levels in the vacuum of space, could have played a role in generating this imbalance. Additionally, the four fundamental forces of nature, gravity, electromagnetism, and the strong and weak nuclear forces might not have been perfectly symmetrical during the earliest moments of the universe. A subtle difference in how these forces acted on matter and antimatter could have tipped the scales. While the exact mechanism behind baryogenesis remains a mystery, scientists are conducting experiments and using advanced particle colliders to look for clues that may unlock this cosmic puzzle. Understanding this process is not just about solving a curiosity, it's about uncovering why the universe exists in the form we observe today. With this mystery in mind, we now move forward to the next profound question: what is dark matter and how did it form? Now turning to the question of dark matter, we venture into one of the most elusive and fascinating mysteries of the cosmos. Dark matter is an invisible substance that does not emit, absorb, or reflect light, making it completely undetectable by conventional telescopes. Despite this, its presence can be inferred through its gravitational effects. It acts almost like an invisible scaffolding, holding galaxies together and influencing the way they move and cluster across vast cosmic scales. Without dark matter, the observed behavior of galaxies simply cannot be explained. Scientists estimate that dark matter makes up about 85% of all the matter in the universe, yet we still do not know exactly what it is. The prevailing theory is that dark matter must have formed shortly after the Big Bang during the universe's earliest moments. As the cosmos expanded and cooled, the particles that might make up dark matter, sometimes referred to as weakly interacting massive particles, could have emerged. These particles are thought to interact only through gravity and perhaps the weak nuclear force, making them incredibly difficult to detect. Ongoing experiments around the world aim to uncover the true nature of dark matter. Particle detectors buried deep underground are searching for rare interactions between dark matter particles and ordinary matter. At the same time, scientists are using massive particle colliders to recreate the extreme conditions of the early universe, hoping to produce these mysterious particles. Space-based observatories are also looking for indirect signs, such as potential signals from dark matter particles annihilating each other in distant regions of space. Despite our lack of direct evidence, the influence of dark matter is undeniable. It shapes the structure of the universe, determines the motion of galaxies, and even plays a role in the way stars form. Solving the puzzle of dark matter will not only answer one of the biggest questions of modern science, but also open a new window into understanding the very fabric of our universe. With this enigma fresh in our minds, we now turn our focus to another invisible force shaping the cosmos: dark energy and how it drives the universe's accelerated expansion. Now turning to the mysterious force known as dark energy, we confront an enigma even more baffling than dark matter. Dark energy is the unseen force driving the accelerated expansion of the universe, and it accounts for roughly 70% of everything in the cosmos. Imagine this: instead of gravity slowing down the universe's growth over time, as one might expect, dark energy causes space itself to stretch faster and faster. This discovery, made in the late 1990s through observations of distant exploding stars called supernova, shocked scientists and completely transformed our understanding of the cosmos. The origins of dark energy are just as mysterious as its effects. Some theories suggest it might have arisen from the energy inherent in empty space, often referred to as the vacuum energy. Other ideas propose it could be linked to an entirely new field or force that we have yet to discover. What we do know is that dark energy's influence likely began billions of years after the Big Bang, when the gravitational pull of matter weakened enough for this force to dominate the expansion of the universe. Its effects are profound, shaping the large-scale structure of the cosmos. It pulls galaxies apart, distancing them from one another at an ever-increasing rate. This means that in the far future, parts of the universe may become so far removed from us that they are no longer visible, effectively disappearing from our observational reach. Some theories even suggest that dark energy could ultimately tear apart all structures in the cosmos if its influence grows unchecked, a scenario often called the Big Rip. Understanding dark energy is not just about explaining why the universe expands the way it does. It is about understanding the ultimate fate of everything around us. Scientists are working tirelessly to find answers, using advanced telescopes to measure the universe's expansion with greater precision, studying the distribution of galaxies across vast scales, and searching for subtle clues in the cosmic microwave background radiation. Each new discovery brings us closer to unveiling this profound mystery. With the stage set by dark energy's far-reaching implications, we now dive into how galaxies themselves formed and arranged into the intricate patterns we observe today. With the next phase of the journey in sight, we explore one of the most captivating chapters in the universe's story, the formation of galaxies and their grand cosmic arrangements. Shortly after the Big Bang, the universe consisted of a hot, dense soup of particles and light. As it expanded and cooled, slight variations in the density of this primordial matter began to form. These tiny irregularities, influenced by the pull of gravity, served as the seeds from which galaxies grew. Over millions of years, gravity amplified these small fluctuations, pulling matter together into increasingly dense regions. It was dark matter, the mysterious and invisible substance making up about 27% of the universe, that played a crucial role in this process. Unlike regular matter, dark matter does not interact with light, but its immense gravitational pull created scaffolding-like structures throughout the cosmos. These cosmic filaments became highways of matter, guiding gas, dust, and stars into clusters and superclusters of galaxies. As stars ignited and galaxies took shape, they organized along these massive web-like filaments, leaving vast, empty voids in between. The result is the breathtaking large-scale structure of the universe we see today, resembling a three-dimensional cosmic web. Within individual galaxies, gravity orchestrated even finer details, drawing gas and dust into disks and triggering waves of star formation. Spiral galaxies, like our own Milky Way, emerged with their elegant, swirling arms, while others formed into more elliptical or irregular shapes. The interplay between gravity, dark matter, and ordinary matter shaped not just the appearance of galaxies but also their distribution across the universe. Observations of galaxy clusters have revealed intricate patterns and connections that hint at the influence of these unseen forces. Even now, galaxies continue to evolve, colliding, merging, and reshaping over billions of years. But how did the very first stars ignite to light up this vast cosmic canvas? Let us turn now to the birth of the stars that brought the universe out of its dark ages and illuminated the heavens. Now turning to one of the most profound remnants of the Big Bang, the cosmic microwave background radiation, or simply the afterglow of the universe's birth. Imagine looking back in time to a period roughly 380,000 years after the Big Bang, when the universe had cooled down enough for protons and electrons to combine into neutral atoms. This dramatic milestone allowed light to travel freely for the very first time, creating a faint glow that permeates the universe to this day. This ancient light, stretched into microwave wavelengths by billions of years of cosmic expansion, is what we now observe as the cosmic microwave background radiation. It is a snapshot of the universe in its infancy, offering invaluable clues about its origins and evolution. By studying the subtle temperature fluctuations within this radiation, scientists have pieced together a map of the early universe, revealing tiny variations that correspond to the seeds of all future cosmic structures. These minute differences in temperature, only fractions of a degree, highlight regions where matter was slightly denser, eventually giving rise to galaxies, stars, and planets. One of the intriguing anomalies within this data is the so-called cold spot, a region that appears significantly cooler than surrounding areas. This strange feature has sparked debates and theories ranging from cosmic supervoids, vast empty expanses of space, to even speculative ideas about interactions with other universes. The cosmic microwave background radiation is not only a relic of the past but also a guide to understanding the universe's deepest mysteries, including its age, composition, and ultimate fate. As we continue unraveling its secrets, we deepen our connection to the origins of everything we see around us. But how did the first stars emerge from this early cosmic canvas? Let us now journey to the era when these luminous giants ignited, transforming the darkness into light. Now turning to the birth of the very first stars, known as Population 3 stars, we encounter a transformative chapter in the universe's story. These ancient stars emerged roughly a few 100 million years after the Big Bang, marking the end of the cosmic dark ages, a period when the universe was devoid of light as no stars had yet formed. Composed almost entirely of hydrogen and helium, the two simplest elements created during the Big Bang, these stars were vastly different from the ones we see today. Unlike modern stars that contain heavier elements, Population 3 stars were incredibly massive, burning their fuel at extreme rates and shining brilliantly but living short, intense lives. Their formation was sparked by tiny density fluctuations in the universe's primordial matter. Gravity caused these regions to collapse, heating the gas until nuclear fusion ignited in their cores, lighting up the universe for the first time. This era, known as the cosmic reionization epoch, was pivotal because the radiation from these early stars began to strip electrons from neutral hydrogen atoms, allowing light to travel freely through the universe once again. These stars played another critical role. They were the forgers of heavier elements. Through the process of nuclear fusion, they created elements like carbon, oxygen, and iron, essential building blocks for planets and life. When these massive stars reached the end of their brief lifespans, they exploded as supernova, scattering these elements across the cosmos, enriching the surrounding gas clouds and paving the way for the formation of subsequent generations of stars and galaxies. The legacy of Population 3 stars is profound, as they laid the foundation for the complex universe we inhabit today. But as their light illuminated the darkness, another mystery arose. How did black holes, some of which became supermassive, form so early in the universe's history? Let us explore this enigma next. Now turning to the question of black holes in the early universe, we uncover one of the most intriguing puzzles in cosmology. Black holes, known for their immense gravitational pull, are regions where matter is compressed into an extraordinarily small space, creating gravity so intense that not even light can escape. But how did these enigmatic structures form in the infancy of the universe? Scientists propose two main types of black holes that may have emerged during this time: primordial black holes and stellar black holes. Primordial black holes are thought to have formed almost immediately after the Big Bang, arising from extreme density fluctuations in the universe's earliest moments. In certain regions, these fluctuations could have been so intense that gravity caused matter to collapse directly into black holes. On the other hand, stellar black holes are believed to have formed later, from the collapse of massive stars like Population 3 stars at the end of their lifespans. However, the real mystery lies in the discovery of supermassive black holes some millions or even billions of times the mass of our Sun, existing when the universe was less than 1 billion years old. Their rapid formation defies conventional understanding, as it would typically take much longer for black holes to grow to such immense sizes. Theories to explain this phenomenon include the possibility of unusually large primordial black holes acting as seeds that rapidly consumed surrounding matter, or the direct collapse of massive gas clouds without forming stars first. Another idea suggests that interactions in dense star clusters could have contributed to their rapid growth. These supermassive black holes are not just cosmic oddities, they play a crucial role in shaping their surroundings. Found at the centers of most galaxies, including our own Milky Way, their immense gravitational influence can regulate star formation and even affect the movement of entire galaxies. While research continues, understanding how these black holes appeared so early in cosmic history remains a key challenge in uncovering the story of the universe's formation. With this enigma in mind, we now move forward to explore another foundational aspect of the cosmos: how the fundamental forces of nature emerged and shaped everything we see today. Moving forward, we delve into the emergence of the fundamental forces of nature, a cornerstone in the story of the universe's formation. In the first fleeting moments after the Big Bang, the universe was an unimaginably hot and dense soup of energy and particles, where the four fundamental forces, gravity, electromagnetism, the strong nuclear force, and the weak nuclear force, were thought to be unified as one. This period, often referred to as the Grand Unification Epoch, represents a time when the laws of physics as we know them today did not yet exist in their current form. As the universe began to expand and cool, these forces gradually separated, a process known as symmetry breaking. Gravity, the weakest of the four forces but dominant on cosmic scales, was the first to emerge, governing the large-scale structure of the universe, including the formation of galaxies and clusters. Shortly after, the strong nuclear force separated, binding protons and neutrons together within atomic nuclei and laying the groundwork for the formation of elements. Next came the weak nuclear force, responsible for processes like radioactive decay, and finally, electromagnetism emerged, a force that governs light, electricity, and magnetism, playing a vital role in chemistry and biology on Earth. These forces are not just abstract concepts, they are the very fabric of reality, working together to shape the universe from the smallest particles to the largest cosmic structures. The interplay of these forces dictates everything from the fusion processes that power stars to the way galaxies interact. However, one of the greatest mysteries in physics remains the question of whether these forces can be unified into a single, all-encompassing theory. This pursuit, often called the theory of everything, continues to drive research into the deepest questions about the universe. Understanding how these forces emerged leads us to the next fascinating layer of the universe's formation, where we explore the role of quantum physics in shaping the cosmos we observe today. Now turning to the role of quantum physics in the universe's formation, we step into the realm of the incredibly small, where the rules of classical physics no longer apply. In the earliest moments after the Big Bang, the universe was not governed by the familiar laws of large-scale physics, but by the principles of quantum mechanics. One of the most fascinating ideas in this area is the concept of quantum fluctuations. These are tiny, random fluctuations in energy that occur in the quantum vacuum, the seemingly empty space that is anything but empty. These minuscule disturbances happening on an unimaginable scale are thought to have played a pivotal role in shaping the universe. Despite their microscopic origins, quantum fluctuations may have been amplified during a period known as cosmic inflation, a rapid and exponential expansion of the universe in its infancy. As space stretched, these fluctuations were magnified, creating density variations in the otherwise uniform early universe. These variations became the seeds for the formation of large-scale structures, such as galaxies and galaxy clusters that we observe today. The intersection of quantum mechanics with general relativity during this period is one of the most intriguing puzzles in modern physics. Quantum mechanics describes the behavior of particles on the smallest scales, while general relativity governs the dynamics of massive objects like planets and stars. However, when applied to the universe's beginning, the two frameworks conflict, leaving scientists searching for a unified theory that can reconcile them. This search has led to groundbreaking proposals like string theory and loop quantum gravity, but a definitive answer remains elusive. Understanding quantum physics in the context of the universe's formation not only shines a light on how the cosmos took shape, but also challenges us to rethink the very foundations of reality. As we unravel this layer of the cosmic story, we are naturally drawn to the question of the universe's age, a key to unlocking its history and evolution. With the next phase of the journey in sight, we turn to the fascinating question of the universe's age. How do we measure the age of something as vast and complex as the cosmos itself? Current scientific estimates place the age of the universe at roughly 13.8 billion years. This remarkable figure is not merely a guess, but the result of observations and calculations made possible by groundbreaking advancements in cosmology. One of the primary tools scientists use to determine the age of the universe is the observation of the cosmic microwave background radiation. This faint glow of light, often described as the afterglow of the Big Bang, carries vital clues about the conditions of the early universe. By studying its temperature and properties, researchers can trace back the timeline of the cosmos to its very beginning. Another critical piece of evidence comes from the universe's ongoing expansion, a phenomenon first discovered by Edwin Hubble. By measuring the rate at which galaxies are moving away from us, known as the Hubble constant, scientists can calculate the time elapsed since the universe began expanding, a cosmic clock of sorts. These two methods, combined with observations of distant galaxies and their light, converge on the same approximate age, reinforcing the reliability of the estimate. However, this estimate is not set in stone. As technology improves and new data emerges, refinements are constantly made. For example, more precise measurements of the cosmic microwave background and the Hubble constant continue to fine-tune our understanding. Slight discrepancies between different methods of measuring the expansion rate have even sparked debates among scientists, hinting that there may still be gaps in our knowledge. Yet, these ongoing efforts to refine the universe's age are not just about numbers. They are about uncovering the story of how the cosmos evolved to become what it is today. This pursuit also reminds us of how interconnected all things are, from the tiniest quantum particles to the grandest galaxies. As we delve deeper into this cosmic timeline, we are left to wonder not only how much we know, but also how much more remains to be discovered. Moving forward, we face the profound mystery of whether the universe is infinite or finite, a question that stretches the limits of our understanding. Now turning to the age-old question of whether the universe is infinite or finite, we enter a realm of profound curiosity and debate. The size of the universe is a question that has intrigued philosophers, scientists, and dreamers for centuries. At its heart lies the challenge of comprehending something so vast that it defies our everyday experiences. One theory proposes that the universe is infinite, stretching endlessly in all directions with no boundaries. This idea suggests that no matter how far you travel, there will always be more universe ahead. An infinite universe aligns with certain interpretations of cosmology, where space itself extends without limit. However, there is also a theory that the universe is finite but unbounded. To imagine this, think of the surface of a sphere. While the surface area is finite, you can travel across it indefinitely without ever encountering an edge. Similarly, a finite, unbounded universe would curve back on itself, creating a space where you could theoretically return to your starting point if you journeyed far enough in a straight line. Scientists rely on geometry to help answer this question. Observations of the cosmic microwave background radiation and large-scale cosmic structures reveal subtle hints about the universe's shape. These observations suggest that the universe appears flat on a large scale, meaning that its geometry does not exhibit significant curvature. A flat universe is often associated with the possibility of it being infinite. Yet, this evidence does not rule out the finite, unbounded scenario, as the curvature might be so slight that it is undetectable with current instruments. The observable universe, the part we can see due to the finite speed of light and the universe's age, offers additional insights. It has a measurable size, spanning roughly 93 billion light-years in diameter. However, this observable horizon is not the full story. It is merely the portion of the universe accessible to us. The regions beyond it remain unknown and could either stretch on forever or exist within a finite but immense boundary. Both possibilities are equally astonishing, challenging the limits of human understanding. As we continue to study these cosmic riddles, we edge closer to uncovering the true nature of the universe's size. But for now, whether the cosmos is infinite or finite remains one of the greatest mysteries of existence. With this vast question lingering in our minds, we next explore another fundamental enigma, the very shape of the universe itself. Moving forward, we arrive at a question that continues to puzzle scientists and inspire imaginations. What is the shape of the universe? At first, this might seem like an abstract concept, but understanding the universe's shape is key to unlocking its overall structure and even its destiny. Cosmologists often describe the shape of the universe in terms of geometry, whether it is flat, open, or closed. A flat universe, as its name suggests, means that space on a large scale follows the rules of flat geometry, where parallel lines remain parallel and the angles of a triangle add up to 180 degrees. This is a concept most of us are familiar with, as it matches our everyday experiences here on Earth. Observations of the cosmic microwave background radiation, the faint glow left over from the Big Bang, strongly support the idea of a flat universe. Measurements of its temperature fluctuations and patterns have shown remarkable consistency with this geometric model. Moving to the open universe theory, this suggests that space curves outward, creating a saddle-like shape. In such a universe, parallel lines would diverge over long distances, and the angles of a triangle would sum to less than 180 degrees. This shape would indicate that the universe is infinite and will continue expanding forever at an accelerating rate. Lastly, a closed universe is one where space curves inward, resembling the surface of a sphere. In this scenario, parallel lines eventually meet, and the angles of a triangle add up to more than 180 degrees. A closed universe would imply a finite cosmos that could potentially stop expanding one day and collapse back on itself in a big crunch. While current evidence from the cosmic microwave background radiation and large-scale structures of the universe points to a flat geometry, the possibility of a slight curvature, whether open or closed, cannot be entirely ruled out due to the limits of our observational precision. Other tools like gravitational wave detectors also provide valuable insights into this question, helping scientists explore how space behaves on the largest scales. As we gather more data, we edge closer to understanding whether the universe is perfectly flat or subtly curved in ways we have yet to detect. Each scenario carries profound implications for our comprehension of the cosmos. With shapes as intriguing as these, the universe once again reveals its ability to defy our expectations. Next, we turn our gaze to a process that shaped the very building blocks of everything we see around us, how elements formed in the universe. Now turning to the creation of elements, we uncover the origins of the building blocks of everything we know. The process of forming elements, known as nucleosynthesis, began in the earliest moments of the universe, just minutes after the Big Bang. During this brief but intense period, the universe was unimaginably hot and dense, a cauldron of energy where fundamental particles collided and fused. This is where the lightest elements, hydrogen and helium, were born, along with trace amounts of lithium. These elements, often referred to as primordial, remain the most abundant in the universe to this day. Hydrogen, the simplest and lightest element, became the raw material for the formation of countless stars and galaxies. But how did the universe progress from these light elements to the heavier ones like carbon, oxygen, and iron that are essential for life? The answer lies within the hearts of stars. As stars are born and evolve, they create extreme pressures and temperatures in their cores, conditions ripe for nuclear fusion. This is the process by which lighter elements like hydrogen fuse to form heavier ones. For example, stars convert hydrogen into helium during their main lifetimes. As they age and burn through their hydrogen supply, they begin fusing helium into even heavier elements such as carbon, oxygen, and neon. However, the formation of elements heavier than iron requires an even more dramatic event. This occurs during supernova explosions, the violent deaths of massive stars. In these cosmic fireworks, temperatures and pressures reach heights that allow the creation of elements like gold, uranium, and platinum. These supernovae scatter these newly formed elements across space, seeding future generations of stars, planets, and eventually life itself. Without these stellar processes, the universe would remain a barren expanse of hydrogen and helium. Instead, stars and their explosive deaths have ensured that the cosmos is rich with the chemical diversity we see today. This cycle of creation and destruction, of stars forging and dispersing elements, continues to shape the universe. With this understanding of how the elements came to be, we can now delve into another profound question. Why is the universe expanding? Moving forward, we now explore the captivating question of why the universe is expanding. This discovery, one of the most groundbreaking in modern science, was made by Edwin Hubble in the early 1900s. Through meticulous observations of distant galaxies, Hubble noticed something extraordinary. Most galaxies appeared to be moving away from us. This led to the realization that the universe itself is expanding, with space stretching and carrying galaxies farther apart over time. Hubble's findings not only revolutionized our understanding of the cosmos, but also provided key evidence for the Big Bang theory. The expansion he observed meant that if we traced the movement of galaxies backward in time, they would converge to a single point, a moment when the universe began. But the story of expansion doesn't end there. In the late 1990s, scientists made yet another astonishing discovery. By studying the light from exploding stars known as supernovae in distant galaxies, they found that the universe's expansion is not slowing down as once thought. Instead, it is accelerating. This unexpected finding introduced the concept of dark energy, a mysterious force that seems to be driving this accelerated expansion. While dark energy is thought to make up about 70% of the universe, its nature remains one of the greatest enigmas in science. It acts in opposition to gravity, pushing galaxies apart at an ever-increasing rate and reshaping our understanding of the universe's fate. The realization that dark energy is not only present but also dominant in the cosmic equation has profound implications. It suggests that the universe will continue to expand indefinitely, growing colder and darker as galaxies drift farther apart, making interactions between them increasingly rare. This discovery challenges scientists to search for deeper insights into the fundamental forces at work in our cosmos. So, while we now have a clearer picture of why the universe is expanding, the mystery of dark energy keeps this field of study alive with questions. With this in mind, let us look ahead to yet another thought-provoking question. Is the universe infinite or finite? Now turning to the enthralling concept of multiverses, we dive into the possibility that our universe may be just one of countless others. The idea of a multiverse suggests that there could be multiple or even an infinite number of universes existing simultaneously, each with its own distinct properties, laws of physics, and perhaps even dimensions. This theory has profound implications for understanding the origins of our universe. It proposes that what we perceive as the beginning, such as the Big Bang, might simply be one event within a much larger framework of cosmic creation. One hypothesis within this realm is the concept of bubble universes. Imagine each universe as a bubble floating in a vast cosmic foam. Our universe is just one bubble among many, with each bubble representing a different universe. These universes might never interact, or they could occasionally collide, potentially creating phenomena we might someday detect. Another intriguing idea comes from string theory, which posits that the fabric of reality is composed of tiny, vibrating strings. In this context, the concept of brane collisions emerges. Branes, short for membranes, are multidimensional objects. A collision between two branes could potentially give rise to a new universe, including our own. Then there is the notion of quantum foam, a concept rooted in quantum mechanics. At the tiniest scales, space and time are thought to be turbulent and frothy, filled with brief, fleeting universes popping in and out of existence. It is possible that one of these temporary fluctuations grew to become our universe as we know it. While these theories are fascinating, concrete evidence remains elusive. Yet, the multiverse theory challenges us to think beyond our observable universe, expanding not only our scientific horizons but also our philosophical perspectives. If there are indeed other universes, each with its own unique reality, it raises profound questions about our place in the cosmos. Could the multiverse be the ultimate answer to why our universe exists, or does it simply reveal an even greater mystery waiting to be unraveled? With these mind-expanding ideas in mind, let us now venture into another cosmic enigma. How does gravity hold everything together? Moving forward, we turn our attention to the invisible but powerful force that binds the cosmos together: gravity. At its core, gravity is the force of attraction between objects with mass, and it plays an essential role in shaping the universe as we perceive it. From holding galaxies together to orchestrating the dance of planets around stars, gravity is the cosmic glue that governs the structure and motion of celestial bodies. Our understanding of gravity took a monumental leap forward with Albert Einstein's groundbreaking theory of general relativity. Einstein proposed that gravity is not merely a force but a curvature in the fabric of space and time caused by massive objects. To picture this, imagine space-time as a trampoline and a heavy ball placed in the center, creating a dip. Smaller objects like marbles would naturally roll towards the ball, illustrating how gravity works on a cosmic scale. This theory helps explain phenomena like the orbits of planets and the bending of light around massive objects, a phenomenon known as gravitational lensing. On the largest scales, gravity plays a crucial role in the formation of galaxies. After the Big Bang, tiny fluctuations in the density of matter allowed gravity to pull particles together, forming stars, planets, and eventually the vast cosmic structures we observe today. Gravity also influences the behavior of mysterious components of the universe, such as dark matter and dark energy. While dark matter appears to amplify the gravitational pull necessary for galaxies to hold their shape, dark energy seems to work in opposition, driving the accelerated expansion of the universe. However, gravity itself still holds mysteries. For instance, scientists continue to investigate how gravity operates in the most extreme conditions, such as near black holes or in the densest regions of the cosmos. Could our understanding of gravity evolve further, revealing deeper insights into the workings of the universe? As we consider these questions, it becomes clear that gravity is more than just a force. It is a key to unlocking the secrets of the cosmos. With this understanding of the gravitational force, we now turn to explore an even more speculative concept. Are there parallel universes? Now turning to the intriguing possibility of parallel universes, we step into a realm that pushes the boundaries of imagination and scientific exploration. The idea of parallel universes, often referred to as the multiverse theory, suggests that our universe may be just one of countless others, each with its own unique laws of physics, dimensions, and even realities. This concept is not merely the stuff of science fiction, but finds roots in serious scientific theories. For instance, some interpretations of quantum mechanics hint at the existence of multiple outcomes branching into separate realities every time a quantum event occurs. Similarly, the theory of cosmic inflation, the rapid expansion of the universe in its earliest moments, proposes that other regions of space-time may have undergone their own inflationary phases, creating entirely separate universes. But how could such universes relate to the conditions of our own Big Bang? One possibility is that the Big Bang itself might not have been a singular event but part of a larger multiverse framework, where each universe emerges as a bubble within a vast, infinite cosmic foam. These bubble universes could have originated from fluctuations in a primordial energy field, leading to initial conditions that vary from one universe to another. Some might resemble ours, while others could be unimaginably different. The evidence for parallel universes, however, remains elusive. Scientists continue to search for signs that could indirectly hint at their existence, such as unusual patterns in the cosmic microwave background, radiation, or detectable effects of collisions between our universe and others. While no such definitive evidence has been found yet, the prospect of parallel universes raises profound questions about our place in the cosmos. Could there be other versions of you or me existing in these parallel realms? And if so, what might their lives look like under alternative conditions? As we ponder these questions, one thing becomes clear. The idea of parallel universes expands our understanding of the universe's formation and challenges us to think beyond the confines of observable reality. With this speculative but fascinating notion in mind, we now ask, what is the ultimate fate of our universe? With the next phase of the journey in sight, we turn our attention to one of the most profound questions in cosmology. What is the ultimate fate of the universe? To understand where the universe is heading, we must first consider the forces and phenomena that drive its evolution. Currently, the universe is expanding, and this expansion appears to be accelerating due to the mysterious influence of dark energy. But what does this mean for its future? Scientists have proposed several theories to explain how the story of the cosmos might end. One possibility is the Big Freeze, where the universe continues to expand indefinitely. As galaxies drift further apart, stars will eventually exhaust their fuel, and new stars will cease to form. Over unimaginable stretches of time, the cosmos would grow cold and dark, a silent expanse of lifeless matter. Another scenario is the Big Crunch, which suggests that the expansion of the universe could one day reverse. If the gravitational pull of all the matter in the universe becomes stronger than the force driving its expansion, the cosmos could begin to contract, ultimately collapsing in on itself. This would lead to conditions similar to those of the Big Bang, raising questions about whether a new universe could emerge from the remnants of the old one. Then there is the more dramatic possibility of the Big Rip. In this theory, the acceleration of the universe's expansion continues to increase over time, eventually tearing apart galaxies, stars, planets, and even atoms themselves as the fabric of space-time stretches beyond its limits. While these scenarios each present a stark vision of the universe's end, they also highlight the intricate balance of forces that have shaped its formation and evolution. By studying these possibilities, scientists gain insights not only into the destiny of the cosmos, but also into the fundamental nature of its origins. Could the ultimate fate of the universe provide clues about how it all began? Or might it suggest that our cosmos is just one chapter in an infinite cycle of creation and destruction? As we contemplate these questions, it becomes clear that the universe's future is as mysterious as its past, reminding us of the enduring quest to understand the vast and wondrous cosmos we call home. Now turning to the question of what might have caused the Big Bang, we delve into one of the greatest mysteries of modern science. The Big Bang represents the moment when our universe began its incredible journey from an unimaginably small, hot, and dense state to the vast cosmos we observe today. But what set this process into motion? One speculative idea comes from the realm of quantum mechanics, which suggests that quantum tunneling could have played a role. In simple terms, quantum tunneling describes how particles can overcome energy barriers that would otherwise seem insurmountable. Some scientists theorize that the universe itself might have emerged from a quantum fluctuation, where a tiny bubble of energy spontaneously appeared and expanded, giving rise to everything we know. Another intriguing possibility is the idea that the Big Bang could have been triggered by the collapse of a previous universe. This aligns with the concept of a cyclical or bounce universe, where the end of one cosmos through a big crunch might set the stage for the birth of another. If this were true, the Big Bang would not signify the absolute beginning, but rather a transition in an eternal cycle of creation and destruction. On the other hand, some philosophers and scientists have questioned whether the universe even needs a cause at all. They propose that the cosmos might simply exist without requiring an external explanation, functioning as a self-contained reality governed by its own internal laws. This perspective challenges our instinct to seek a cause for everything and asks us to consider the possibility that the origin of the universe might transcend the limits of human understanding. These ideas, while speculative, provide incredible insight into the creativity and curiosity driving scientific exploration. They remind us that the mystery of the universe's origin is not just a scientific question, but also a profound philosophical one. Could the answer to this riddle lie in the interplay between science and philosophy, or is it a question that may forever elude us? As we ponder these possibilities, one thing remains clear. Exploring what might have caused the Big Bang opens doors to a deeper appreciation of the universe's grandeur and our place within it. Moving forward, let us consider a truly mind-bending possibility. Could the universe's beginning, including the Big Bang, be part of a vast simulation? The simulation hypothesis proposes that what we perceive as reality might actually be a highly advanced artificial construct, designed and controlled by an intelligence far beyond our comprehension. Under this theory, the Big Bang could be seen not as the start of a natural cosmos, but as the initialization event of an intricately programmed system. To make sense of this, imagine a computer simulation, much like a video game, where the universe begins with certain programmed parameters that dictate the laws of physics, the behavior of particles, and the eventual evolution of galaxies, stars, and planets. If such a simulation were possible, it raises profound philosophical and scientific questions about the nature of existence itself. Could the appearance of randomness and natural processes in our universe actually be the result of coded algorithms? And if so, what would be the purpose of such a simulation? Some suggest it might be a form of research by an advanced civilization, a way to study the development of life and consciousness. Others speculate that it could be a form of entertainment or even a reflection of ethical or moral experimentation by its creators. The implications are staggering. If we are living in a simulation, it could mean that our understanding of the universe's formation is inherently limited to the rules set by the creators. This idea prompts us to reconsider the Big Bang as not just a scientific event, but potentially the moment when the simulations program began running. While this hypothesis remains highly speculative and currently untestable, it has sparked serious discussion among philosophers and physicists alike. It forces us to question the very foundations of what we consider real, and whether the search for the universe's origin might eventually lead us to answers beyond the realm of traditional science. Could the simulation hypothesis be the key to understanding the ultimate nature of reality, or is it merely a fascinating but unprovable thought experiment? Either way, it opens a window to new ways of thinking about the cosmos and our place within it. Now turning to the perplexing enigma of dark matter and dark energy, we find ourselves at the frontier of cosmic discovery. These two mysterious components make up about 95% of the universe, yet scientists remain in the dark, both literally and figuratively, about their true nature. Dark matter, an invisible substance, is believed to act as the scaffolding holding galaxies together through its gravitational influence. Dark energy, on the other hand, is theorized to be the driving force behind the accelerated expansion of the universe. But how close are we to unraveling these cosmic puzzles? The search for answers is unfolding through groundbreaking experiments and innovative technologies designed to push the boundaries of our understanding. For instance, particle detectors buried deep underground are hunting for elusive particles thought to make up dark matter, while experiments onboard the International Space Station aim to detect subtle signals of its presence in the cosmos. Meanwhile, powerful telescopes and observatories, such as the James Webb Space Telescope, are providing unprecedented views of the universe, helping researchers study the effects of dark energy on the large-scale structure of space. Looking ahead, future projects like the Large Synoptic Survey Telescope and next-generation particle colliders may offer game-changing insights. Theoretical breakthroughs could also emerge as physicists strive to reconcile quantum mechanics with Einstein's theory of general relativity, a step that may hold the key to understanding these phenomena. If successful, such discoveries would not only redefine our understanding of the universe's formation, but could also revolutionize fields like energy, technology, and our approach to fundamental questions about existence. Imagine a day when we could manipulate dark energy or harness the properties of dark matter for practical use. This would represent a quantum leap for humanity. While the path to uncovering these cosmic secrets is fraught with challenges, the pursuit itself is a testament to human curiosity and ingenuity. Could dark matter and dark energy hold the answers to the universe's deepest mysteries, or are they clues leading us to an even greater cosmic revelation? Only time and relentless exploration will tell. With the next phase of the journey in sight, let us delve deeper into the concept of the multiverse and its profound implications. If multiple universes exist, each could operate under its own unique set of physical laws, dimensions, and constants. Imagine a universe where gravity is stronger, stars burn out more quickly, or even one where life as we know it could never arise due to entirely different atomic foundations. This notion not only challenges the boundaries of cosmology, but also pushes the limits of our philosophical understanding. What does it mean for our universe to be one among countless others? Could the multiverse explain why our cosmos seems fine-tuned for life? The idea of bubble universes, for example, suggests that each universe within the multiverse may have emerged from a different quantum fluctuation, leading to a distinct reality. Some theories posit that these universes may occasionally interact in subtle ways, leaving faint imprints or anomalies in the cosmic microwave background radiation, clues that scientists are actively searching for. But the implications go far beyond science. Philosophers ponder whether the multiverse would diminish the uniqueness of our existence or, conversely, enhance our understanding of existence itself. If other universes indeed exist, it opens the door to questions like whether versions of ourselves could inhabit them, leading to fascinating debates about identity, choice, and reality. Exploring the multiverse could one day redefine the way we view everything, our place in the cosmos, the meaning of life, and the nature of reality itself. And as we continue to refine our theories and develop advanced observational technologies, we may inch closer to uncovering evidence of these other realms. Could the multiverse reveal the ultimate truth about why anything exists at all? As we stand on the precipice of this grand mystery, we are reminded of the infinite possibilities that the cosmos might hold. Moving forward, let us consider how gravity, the force that anchors our universe, plays a role in shaping the vastness around us. Now turning to the tools and methods that bring us closer to understanding the universe's earliest moments, we find ourselves at the forefront of scientific ingenuity. Particle colliders, such as the Large Hadron Collider, allow scientists to recreate conditions similar to those just fractions of a second after the Big Bang. By smashing particles together at incredibly high speeds, researchers can study the fundamental building blocks of matter and uncover clues about how the universe began to take shape. These experiments shed light on forces and particles that existed in the universe's infancy, offering a glimpse into a time before stars, galaxies, or even atoms had formed. Equally fascinating are gravitational wave observatories, which detect ripples in space-time caused by cataclysmic cosmic events. These faint distortions not only provide insights into phenomena like colliding black holes, but may also hold the key to understanding the universe's very first moments. Scientists believe that certain patterns in gravitational waves could reveal what happened during the earliest fractions of a second after the Big Bang, potentially offering evidence for theories like cosmic inflation. Satellite-based telescopes represent yet another critical tool in this quest. Instruments like the James Webb Space Telescope are designed to peer deep into the cosmos, capturing light that has traveled for billions of years to reach us. This light acts as a time machine, offering a direct window into the young universe. By studying the first galaxies and stars, astronomers hope to reconstruct the sequence of events that followed the Big Bang, piecing together the story of how structure and complexity emerged from the initial chaos. Yet, despite these advancements, many mysteries remain hidden. What exactly powered the Big Bang itself? How did the early universe transition from an almost featureless state to one brimming with stars and galaxies? Could there be unknown forces or particles that shaped these earliest moments? As technology advances and our methods grow more refined, we edge closer to unraveling these cosmic enigmas. Each discovery has the potential to rewrite what we think we know about the universe, pushing the boundaries of human understanding into realms we can only begin to imagine. With these tools and questions in mind, let us now explore the force that governs all of this, the role of gravity in holding the universe together while shaping its breathtaking complexity. Moving forward, let us consider an intriguing question. Could the universe's formation be explained without the Big Bang? While the Big Bang theory remains the most widely accepted model, alternative ideas have been proposed over the years, each challenging our understanding of the cosmos. One such hypothesis is the steady-state theory, which suggests that the universe has no beginning or end. According to this idea, as the universe expands, new matter continuously forms to maintain a constant density. This theory was popular in the mid-20th century, but mounting observational evidence such as the discovery of the cosmic microwave background radiation and the observable evolution of galaxies made it difficult to support. Another alternative is the cyclical universe model, which envisions a series of infinite cosmic cycles where the universe undergoes periods of expansion and contraction. In this perspective, the Big Bang could be seen as a transitional event between a previous collapsing universe and our current expanding one. Although compelling, this theory raises questions about what could drive such cycles and whether evidence of past universes could ever be detected. A more speculative idea comes from quantum physics, suggesting that the universe could emerge spontaneously from a quantum vacuum, a state where particles and energy exist fleetingly in fields of uncertainty. This concept aligns with some interpretations of quantum mechanics, but remains highly theoretical due to the difficulty of testing it. Despite these fascinating alternatives, the Big Bang model continues to dominate scientific consensus because it best fits the extensive data we have, from the cosmic microwave background to the observed distribution of elements like hydrogen and helium in the universe. However, even the Big Bang theory is not without its challenges. For instance, it cannot explain what caused the Big Bang or what, if anything, might have existed before it. These unanswered questions remind us that our understanding of the universe is still evolving, and new discoveries could one day refine or even replace the frameworks we rely on today. As we reflect on these alternative ideas, it is clear that the quest to understand the universe's origins is far from over, inviting us to remain curious and open to the possibilities that lie ahead. As we journey through these 20 profound questions about the formation of the universe, one thing becomes undeniably clear. The story of the cosmos is as much about mystery as it is about discovery. Each answer we uncover seems to open the door to even more questions, inviting us to continue exploring the vast expanse of space and time. From understanding the Big Bang and the enigmatic forces of dark matter and dark energy to contemplating the possible existence of multiverses or the fate of everything we know, the quest to understand the universe is far from complete. It is this very sense of wonder and curiosity that drives science forward, reminding us of how much there is still to learn. So, what do you think? Could there be answers hidden in the fabric of space waiting to be found? Or might the true nature of the universe always remain just out of reach? Let us know your thoughts and theories in the comments below. If you enjoyed diving into these cosmic mysteries, be sure to like this video, subscribe to the channel, and turn on notifications so you never miss an opportunity to explore the universe with us. Together, let us continue to search for answers among the stars. Thank you for watching, and until next time, keep wondering and keep exploring.